Francesco Benini from the Simon Center, and the title of his talk is M2-branes at toric Calabi-Yau 4 singularities.
Okay, so first of all, I would like to thank the organizers for the invitation here to speak. Moreover, okay, this is a talk with slides. Maybe it's not the best choice for a workshop like this, but I'd like anyway to keep the discussion informal, so please interrupt at any time with question and comment. Okay, and this is some work done in collaboration with Cyril Crosset at the Weizmann Institute and Stefano Cremonesi at Imperial College. Okay, so I will talk about some examples of ADS4 CFT3, and the basic example of ADS4 CFT3 comes from considering the low energy dynamics on a stack of n and M2-branes in M theory. In fact, this is a system that gives us a three-dimensional theory with n equal 8 superconformal symmetry, and one way to know that the system is superconformal is to look at the near horizon geometry of an M2-branes in 11-dimensional supergravity, and one can find the following supergravity solution. It was written long ago. This is a Freund-Rubin compactification on S7. And there are some units of G-form flux on the S7. More importantly, there is an ADS4 factor, and this tells us that the low energy dynamics must be conformal. Now, it took a long time to find a field theory description of these low energy dynamics. In fact, it's not obvious that such a description exists, but in fact, it was found. And this is work now famous of Bagger-Lambert, Gustafsson, and then Aroni, Bergman, Jafferis, and Maldacena. So I will mainly focus on the ABJM proposal, although it's been shown to be equivalent to the Bagger-Lambert proposal. And the proposal of ABJM that now is famous is as a quiver Chern-Simons theory. So let me remind you what this proposal is. So what they do is that, okay, they consider a slight generalization of flat spacetime. So they consider M2-branes on an orbifold of flat spacetime, for k equal to 1 recovers flat spacetime. And their proposal is that the low energy theory is a quiver, which is represented by this quiver diagram. There are two gauge groups represented by these circles. It is a Chern-Simons theory. So there are some Chern-Simons levels, which are k minus k. And then there is some matter, some bifundamental matter, which is represented here by these arrows. There is also some superpotential, which looks like this. And now, okay, one could observe that this, in fact, is the same quiver and superpotential that appeared before in the conifold theory of Klebanov and Witten. And in fact, this is not a coincidence. In fact, the field theory can be derived with a Hanani-Witten construction in type 2b, which is very similar to what was done, what can be done for the conifold theory. Okay, so this is the prototypical example of ADS4 CFT3, and I want to talk about generalization of this example. However, before going on with talking about what I want to talk, I would like to point out that, okay, one could think that ADS4 CFT3 could just be a repetition of ADS5 CFT4 in just one dimension less. And so from that point of view, could be, okay, not so interesting. But in fact, I would like to point out some differences between the four-dimensional, or better, between the three-dimensional and the four-dimensional case, in order to give you some motivation for why this case, this dimensionality is in fact quite interesting. Okay, so first of all, the three-dimensional theory, and you can think of the ABJM example, is a Chern-Simons matter theory, is not a Young-Mills theory. And so in particular, it contains a topological sector. And for this reason, people have considered applications of this theory to condensed matter problems. For instance, quantum Hall, topological insulator, or systems that can realize edge states, and so on. Another difference is that in 3 dimensions, there are local operators called monopole operators, which are not local functions of the fundamental fields, at least in the non-abelian theory, but rather they are a boundary condition in the path integral. So they are similar to 't Hooft line operators in 4 dimensions, but they are local in 3 dimensions. And so they introduce some new dynamics if one study local operators that is not there in 4 dimensions. Well, in 3 dimensions, if you have gauge symmetries, in particular abelian gauge symmetries, there are topological symmetries. So these are symmetries for which one can construct the current. It's just the dual of the abelian field strength. But one cannot see manifested in the Lagrangian the symmetry. So this is not another current, it's a topological current which is topologically conserved. This is again something that is new with respect to 4 dimensions. And moreover, what can happen in the quantum theory is that actually these topological symmetries, which are abelian, can actually enhance to form non-abelian symmetries. And these are called hidden because for these enhanced symmetries, not only the symmetry, the action of the symmetry, but even the current are not manifest. In fact, they correspond to monopole operators. Okay, another direction is that if one has some supersymmetry, at least n equal to supersymmetry, one can compute the so-called S3 partition function, which is the path integral on S3, and there have been many talks about this in this workshop so far. And this can actually be explicitly computed with localization techniques. It reduces to a matrix integral. Now, the same computation can be done in 4 dimensions, so a partition function on S4, but it turns out that in 3 dimensions the result is much easier because it is not a sum over instantons, it's just a simpler matrix integral. And for this reason, there has been a lot of work in studying the properties of this partition function. Okay, so these were differences mainly, well, from the field theory point of view. Now I would like to point out some differences from the gravity point of view. So from the gravitational point of view, well, we have a supergravity solution, which is ADS4 times some Sasaki-Einstein 7 manifold, if we have a supersymmetry, more generally a 7 manifold. Now, suppose that this 7 manifold has some 4th cohomology, and this 4th cohomology contains some torsion group. It can be just torsion, or it can contain some torsion group. Now, in this case, one can turn on some flux along this torsion group. Now, this flux is flat. Essentially, this is a flat connection. For this reason, it doesn't introduce energy, and so one still finds ADS4 solution. So, from the field theory point of view, one expects that for each element of this torsion group, one should be able to find a conformal field theory. And so one should find a family of conformal theories. This is, if you want, different from 4 dimensions, because in 4 dimensions, there are no torsion factors in general. So if one introduces some flux, introduces energy, and so the supergravity is deformed, and there is no longer ADS. In general, there are cascading solutions or other types of solutions. Finally, another difference is that in ADS4, vectors can enjoy a double quantization, much like scalars can enjoy a double quantization more or less in all dimensions if the mass is in the correct range. And so changing this quantization corresponds to changing the boundary conditions for these fields, and in particular changing the boundary condition for a vector in DS4 corresponds to having some global symmetry, engaging this global symmetry. So for instance, this has been used by some people to compute holographic solution that represents vortices in superfluid and superconductors. The difference is precisely that in one case there is a global symmetry which is broken in the superfluid. In the superconductor this is gauged. And so people observe that vortices behave in a rather different way. In particular, for superfluids there is the energy is logarithmically divergent. For superconductors the energy is finite. Okay. So these were some motivations in order to make ADS4C53 interesting. Okay, any questions so far? Okay, good. So what I want to look at is generalization of this prototypical example of BGM to lower supersymmetry. well, in general, if one lowers the supersymmetry, there is less control on the theory, but on the other hand, there is richer dynamics. So for instance, one can go down to n equal 4 supersymmetry. Remember, we started with n equal 8, or in the case of the orbit for n equal 6. So in this case, one can prove that the geometry will be a quotient of R8. There is a sort of classification. One can go down to n equal 3. In this case, the 7 manifold is the section of a hyperkähler cone. And in most examples of pairs with n equal 3 supersymmetry, in fact, the field theory can be found with an M2-brane construction. Now, if you go down to n equal 2 supersymmetry, the geometry is going to be a Calabi-Yau 4. And in the literature, there has been many proposals for various Chern-Simons quivers, which are dual to various geometries. However, in most cases, there is no Anani-Witten construction, and so there is no systematics involved. In most cases, it's a work of guessing. So what I'm interested in is to see if one can build some other brane construction and introduce some systematics in the way of finding the field theory for Calabi-Yau for singularities. Also, let me point out what are some requirements that the dual field theory should have. This is in the spirit of, okay, if we come up with some proposal, then we want to do checks. What are the checks that one can do? Well, of course, the modular space of the field theory should contain some symmetrized copies of the Calabi-Yau 4, if this is going to describe the motion of n and 2 branes on the Calabi-Yau 4. The field theory should also describe all Krepan resolutions of the Calabi-Yau 4. We can resolve the Calabi-Yau 4 in various ways, and these should appear as either modular space or parameter space of the field theory. Moreover, when the Calabi-Yau 4 admits some torsion fluxes, actually the field theory should come in families, and the number of members in the family should precisely match with the set of torsion fluxes that one can put on the geometry. And then, in principle, there are other more refined checks, which are very, very interesting. One is computing, for instance, the S3 partition function and see whether it reproduces the behavior n to the 3 halves. It should also reproduce the volumes of supersymmetric cyclones, supergravity. Or could also compute the index, which is the path integral on S2 times S1, and see whether this reproduces the index of gravitons in supergravity. Okay, so the first goal is to try to come out with some brane construction to derive the field theories. Okay, there is a second issue here because well, the first two checks were referring to computing the modular space of these field theories, and this is not completely trivial task. The reason is the following, that in three-dimensional gauge theories, as I said, there are local monopole operators, and if we have at least n equal 2 supersymmetry, then there are BPS monopole operators. So they appear in the chiral ring, but actually they are necessary to generate the full chiral ring. And the reason is simple, because they are charged under topological symmetries. Fundamental fields are not, so they are necessary to generate sectors in the chiral ring, which are graded by the topological symmetry. So we need to take into account these monopoles. Now, let me consider a very simple example. For instance, some abelian quiver as a product of U1 gauge groups. And let me consider the simplest monopoles, I will call them T and T tilde. So T has 1 unit of flux in each of these U1, so a sort of diagonal monopole. And T tilde is minus 1 unit of flux in each of these groups. Now, classically, one can write these monopoles, and for this abelian quiver, as exponentials of the dual photon. So phi is the dual photon. And so in particular, one sees that they satisfy a simple relation, which is T tilde is equal to 1. So in fact, classically, one can actually forget about these monopoles, directly use the dual photon. Actually, the dual photon can be gauge fixed, and so one can actually work just with the fundamental fields and, in the theory. So this has been applied by BJM and then more generally by Martelli-Sparks. Essentially, one loses part of the gauge symmetry because it's gauge fixed in this dual photon, but at the end of the day, it just computes the classical modular pair in terms of the fundamental fields. However, in the quantum theory, it can happen that these monopoles, T and T tilde, can get charges. for instance, R charges, flavor charges, gate charges. And so in particular, it can happen, and in general it does happen, that this relation can no longer be true just because T tilde is not neutral, so it cannot be equal to 1. And so in general, in the chiral ring, there are some quantum deformed relations of the following form in which O1 and O2 are some strings in the fundamental field. So the second question I want to pose is how do we apply this to compute the quantum modular space of these quivers? Okay, so a nice proposal for an alternative brane construction to the one of a BJM to get the field theory was given by Aganagic. And the proposal is the following. So suppose that we want to study M2-branes at a Calabi-Yau 4 singularity, which is a conical singularity, so it's a cone over some Sasaki-Einstein manifold Y7. Now suppose that Y7 has some isometry that we call U1M, then we can do the reduction to type 2A. So in type 2A we'll have some 7 manifold, which is the quotient of the Calabi-Yau 4 by this U1. Now if this is possible, and in general this is not possible, if this is possible, choose the U1M first of all in such a way that it's not the Rib vector. In fact, any Sasaki-Einstein 7 manifold has a U1M, but we don't want to use this direction which is always there, because if we reduce along that direction we break supersymmetry because the Killing spinors are charged under this direction. So suppose there is another one, and suppose that one can choose this other one in such a way that the Keller quotient of the Calabi-Yau 4 by this one is a Calabi-Yau 3. Now if this is the case, something nice happens. So what happens is the following. So we don't want to do the Keller quotient, we want to do the ordinary quotient. And so in fact the geometry one can get in type 2A is a fibration of the Calabi-Yau 3 sitting here along the real line that I will parameterize by R0. So the geometry is a 7 manifold. There is a real line R0. At each point of the real line there is a Calabi-Yau 3. And as we move along this real line, the Keller moduli of the Calabi-Yau 3 are piecewise linear functions. So the volumes of the Calabi-Yau 3 are changing. The Calabi-Yau 3 is blown up, and the volume of these, for instance, 2 cycles is piecewise linear with R0. The reason is that, as I say, we don't want to do the Keller quotient. Now in the Keller quotient there is one has to choose a level in the moment map. We don't want to fix this level of the moment map, so we keep it as one of the coordinates. It will be R0. And so as we change the level of the moment map, one gets a foliation of this X7 by Calabi-Yau 3. Okay, so this is the kind of geometry one gets in type 2A. And then, well, this U1M, under which we reduced, we have some first chain class on X7, and this, with the reduction, corresponds, give rise to some two-form flux in type 2A. So this is the kind of geometry we get. So this is good enough to try to understand what the field theory is, because now we have, well, we have also the M2-branes. They become D2-branes. So now we have some D-branes, D2-branes at a Calabi-Yau 3 singularity, and we know that this is described by a quiver gauge theory. This is because the D2-branes breaks up at the singularity into fractional branes, like D4 on 2 cycles and D6 on 4 cycles. So first of all, we have a quiver with a superpotential. But then also we have something else, because we have some two-form flux, and one can see that the Verzumino term, for instance, suppose we have a D4 on a 2 cycle, from this Verzumino term, the integral of F2 gives precisely a Chern-Simons term. So we get Chern-Simons terms, and one can see that actually from the dBi there is another term that gives the bosonic, the n=2 bosonic completion of this. So at the end of the day, one gets an n=2 quiver Chern-Simons theory. So this sounds perfect. We have a method to derive the field theory in all cases. But unfortunately, there are some difficulties here. There are two main difficulties in trying to apply this program. The first problem is the following. So we said, okay, we need that there is some U1M, which is not the Rib vector, and such that it produces a Calabi-Yau 3 by reduction. And in general, there is no such a thing in a Sasaki-Einstein manifold. If we want to have a setup in which there is always such a thing, one class of geometries is toric geometry. So in toric geometries, the Calabi-Yau 4 has 4 of these U1 isometries. And so in particular, among these 4s, one of them is the Rib vector, one is left with 3. And one can choose a subset of these in such a way that the Keller quotient is a Calabi-Yau 3. So first of all, there is always a solution for these problems. So there is always a U1M that can be used. Actually, there is more. There is some parameter space of them. There is more than one. And so in principle, one could hope to have different reductions to type 2A that possibly give rise to some equivalent descriptions. So one can hope to find mirror descriptions of this three-dimensional, or some other dual description of this three-dimensional theory. Actually, toric geometry solves another problem, which I didn't mention before, is that, okay, I said when we have D-branes at a Calabi-Yau 3, we know that this gives rise to a quiver, but in general, we don't know the answer to this problem. However, if we have a toric Calabi-Yau 3, which is what we obtain if we start with a Calabi-Yau 4 and we do a Keller quotient, then we always know what is the quiver description of the branes at the Calabi-Yau 3. So essentially in toric geometry we solve these two problems at once. Good. So let's restrict to toric geometry. However, still there is another problem that, of course, when we do the reduction, we have to keep into account all possible singularities that we find in type 2A. One class of singularity was the M2-branes that comes from the M2-branes, but there can be more. In particular, so for instance, suppose that this U1M action degenerates somewhere, then we know that when we do the reduction, we get the D6-branes in type 2A. So these D6-branes have to be taken into account, and that will be the main subject of my talk. However, there can be other singularities that appear in type 2A. In particular, it can happen that not the full U1M, but just a discrete subgroup of it degenerates. And if this happens, one gets some more nasty singularity in type 2A, and a singularity that we don't understand very well. So in these cases, this problem cannot be applied. So this poses a limitation to the class of geometries to which the problem can be applied. Okay, so well, this is the program that I want to apply to find this U1M, doing the reduction and rid of the field theory. And actually, since we want to restrict ourselves to toric geometry, we can use some more powerful tools that appear in toric geometry. So in particular, a toric Calabi-Yau 4 can always be represented as some gauge linear sigma model, or more general quotient gauge linear sigma model. That means that we, I mean, it's completely defined by a set of variables, T1 to Tn, and a set of gauge symmetries, abelian gauge symmetries. They are n minus 4 in such a way that when we mod out by this, I mean, when we solve for the modular space of this theory, we find out something which is 4-dimensional. And if the charges are such that they sum to 0, we get a Calabi-Yau 4. So every toric Calabi-Yau 4 can be represented in this way. Now, we want to compute this Keller quotient by U1M, and it's very simple. We just have to add another row here, given by some charges. And whenever these charges sum up to 0, then we get a Calabi-Yau 3. So this gives us a parameterization of the choices of reductions that we can use to apply our program. And from here, we also had a better understanding of the geometry, because here there are Fourier-Tiliopoulos terms. So when we compute the D terms of these gauge groups, we have to set, I mean, we have some Fourier-Tiliopoulos appearing into the D term equations. In particular, here, there is a Fourier-Tiliopoulos that I called R0. And as I said, we don't really want to do the Keller quotient. We want to do the ordinary quotient. So we keep this R0 as our coordinate. And as we vary this R0, we get our fibration of the Calabi-Yau 3 along the line. And well, we know that these Fayette-Iliopoulos in fact control the Keller moduli of the Calabi-Yau tree. Okay. Any questions so far? Good. Okay, actually in toric geometry we have even more power because we can understand a lot of geometries with diagrams, toric diagrams, and so in particular this becomes very helpful in doing these reductions. So in particular, the toric diagram of a Calabi-Yau 4 is a three-dimensional polyhedron, a convex polyhedron. And here is one example, for instance, a sort of pyramid. This is the toric diagram of C4. And now, in order to do this scalar quotient, we just have to go in a basis in which this UNM corresponds to a vertical direction. And then the scalar quotient by UNM is just the vertical projection of this toric diagram to the plane. This gives a two-dimensional diagram, and this is the toric diagram of the Calabi-Yau tree. So for instance, here, if I do this reduction now, I get a square, and the square is the toric diagram of the conifold. So this is a scalar quotient of C4 that gives the conifold. Okay. So the diagram is also helpful in understanding what kind of singularities we get into the reduction. In fact, every time we have two vertically aligned points in the three-dimensional diagram, and we do the reduction to type 2a, we get a D6 brane. This is because we can consider a simple example of C4 with some action of UNM, which is just this one, and we know this is the action of UNM of Taubnat, such that when we do the reduction, we get a D6 brane. Okay, so, but this applies more generally. So when we have this toric diagram, every time we have vertical aligned points, we do the reduction with the D6 branes. Now, these D6 branes are wrapping some toric divisor in the Calabi-Yau tree, and the divisor precisely corresponds to the point in the two-dimensional toric diagram to which these vertical aligned points project. So we can even identify very easily where the D6 brane is sitting. Now, there are two situations can happen. One is that this point to which the vertical aligned points project is an external point of the two-dimensional toric diagram. In this case, the D6 branes wrap a non-compact divisor, and they give rise to some flavors in the quiver. The other case that can happen is that this is actually an internal point, and so the D6 branes are wrapping a compact divisor, and so they give rise to what is called anomalous fractional branes, and they correspond to having unequal ranks in the quiver. Okay, so let me spend a few more words on these two cases, explaining some more details what is going on here. So let's look first at the case of non-compact D6 branes. So suppose we have, well, more generally, P+1 vertically aligned points, and they project to the same external points of the two-dimensional toric diagram. Then we get P non-compact D6 branes. As I say, they wrap a non-compact toric divisor, and so they introduce flavors into the quiver. In particular, they introduce a pair of flavors, Q and Q tilde. Now, these flavors will be coupled to some chiral fields in the quiver. They can call Xij, and there will be some superpotential coupling the flavors to the field in the quiver. This is a bifundamental. And also there will be some half integral shift of the Chern-Simons level. Okay, so this is the kind of theory that we get, essentially a quiver with flavors. We can actually be a little bit more precise about what field in the quiver they are coupling to. And moreover, notice that once we specify which is the bifundamental, we also know what are the charges of these quarks, because of course they have to couple to this bifundamental in the quiver. So what happens in general is the following, that given a non-compact toric divisor in the Calabi-Yau tree, this is due to a collection of bifundamental fields in the quiver, and there are Q of them, and Q depends on the particular divisor. And the reason why we have Q of them and not just one is the following. The toric divisor has some section which is a length space, S3 mod ZQ, and the D6 branes are wrapping this manifold. And so in particular, one can turn on flat connections on the D6 branes. They don't increase the energy, and there are Q of them, and so turning on this flat connection corresponds to selecting one of these fields in the quiver. So selecting this, specifying some flat connection in the D6 changes the gauge charge of these quarks and where they are attached in the quiver. And now we can even uplift to M theory this torsion flux on the D6, uplift to torsion flux in M theory, and so we see how in this class of example torsion flux appears. So it corresponds to giving different gauge charges to the flavors and changing the superpotential. And here I'm being quite general and abstract, but this can be worked out very explicitly in examples. So in particular, let me consider a simple example just to give you a flavor of what is going on. So suppose I consider this geometry. Here is some toric diagram of some fourfold. And here I have some vertical aligned points. In particular, if I have just two of them, this geometry has a name. And it has a name because the metric is known. Now we just apply the program. So we do the vertical projection. If we do a vertical projection, we get a square, which corresponds to the conifold. So we should get the quiver of the conifold. Moreover, there are these vertical aligned points that corresponds to flavors, and so we should get a flavor version of the conifold. In fact, the field theory is the following. This is the conifold quiver, and here are the flavors. I represent them with a square. A square means that I have some global symmetry instead of some gauge symmetry. And here is the flavors. And in fact, they are coupled to one of the fields in the toric diagram, which in this case is A1. In particular, these flavors carry some flavor group, UH, and this in type 2A precisely corresponds to the fact that we have some non-abelian fields on the D6 branes, some UH gauge field. And now, okay, so what one can do is compute the modular space of this quiver with the techniques that I will explain in a moment, and reproduce this geometry. And one can also understand various deformations in the solution of the Calabi-Yau 4 as corresponds to giving real masses to the flavors. Any question on this example? All right. Now I would like to consider the other case, the case in which the vertical aligned points project to some internal point in the two-dimensional toric diagram. And again, I'm considering this example. This is a sort of, well, I don't know, some convex polyhedron. In this case, the vertical projection is a triangle. And in particular, this is, well, in this case, is the quiver, is the toric diagram of C3 mod Z3, so very simple Calabi-Yau 3. And here we have some vertical aligned points. They project to an internal point of the two-dimensional toric diagram. Again, the two-dimensional toric diagram is this triangle here. And so they give rise to some D6 brane, in this case just one, which is wrapping a compact exceptional divisor of the Calabi-Yau 3. This is, in this example, the Calabi-Yau 3 is C3 mod Z3, and so the fourth cycle is the CP2, which can be resolved in the geometry. Now, using four-dimensional language, language that we have if we consider the D3 branes at a Calabi-Yau 3 singularity, these kind of branes, which are wrapping a compact divisor, are called anomalous fractional branes. And they give rise to unequal ranks into the quiver. Now, why they are called anomalous fractional branes? Well, because if we try to do the same in type 2b, so we have a Calabi-Yau 3, we put D3 branes instead of D2, and we try to get a four-dimensional theory. Again, we could try to wrap D7 branes in that case on the fourth cycle, or more generally also D5 branes on the two cycle. However, what happens is that we get a tadpole. Because there is some Ramond-Ramond flux, which is generated by these branes, that is not cancelled. And this, in the four-dimensional gauge theory, corresponds to the fact that if we change the ranks of the quiver, the ranks of the gauge groups in the quiver, we get chiral gauge anomalies. So we have some inconsistent configuration on both sides. For this reason, these are called anomalous fractional branes. However, in type 2A, the geometry really has this extra direction, R. So it was Calabi-Yau 3 fiber along this direction, R. So really, the Ramond-Ramond flux can escape, so there is no tadpole. And on the other hand, in 3 dimensions, there are no chiral gauge anomalies. So in 3 dimensions, this configuration makes perfect sense, and I will keep calling them anomalous fractional branes, but really there is nothing anomalous here. Moreover, these branes have not been studied much in 4 dimensions precisely because they give rise to some inconsistent configuration. Okay. So as before, I would like to consider one simple example to understand what is the physics and what is going on. Yes?
If we forget about the toric vortex at top on the left-hand side, this is nothing but a toric diagram for flat plate C4.
Yes.
So when we do this projection down to 2D,
Yes.
since that this vortex along the jet line project down to the same, I mean,
Yes.
there is what happens in this case?
So what happens in that case is precisely that one can have 2 mirror description of the theory from C4. So one is the one that represents the beginning. So you do the projection such a way that you get the conifold, and this is a BJM at level 1. The other one is precisely that you can take just this one, you project down, and you get the toric diagram of C3. This is the toric, the quiver diagram of n equals 4. But you also have one flavor. So you get that there is one extra flavor coupling to one of the adjoints. And this is a mirror description of a BJM at level 1. So this is precisely one example in which doing different reductions, you can have mirror descriptions. All right. Okay. So I would like to consider some simple example and study more detail to understand precisely the details of what is going on. A sort of prototypical example of these anomalous fractional branes. And so let's consider a class of geometries of Sasaki-Einstein 7 manifolds. They are called YPQ. They've been introduced by Gonter, Martelli, Sparks, and Waldram. They have a name because the matrix is known. And if one considers the cone over this, one can have Calabi-Yau 4. So this is a 2-parameter family because one can choose integers p and q. Okay, so let me give you some properties of these geometries. Okay, so first of all, they are S3 mod ZP bundles over CP2. So P controls the fiber. On the other hand, Q controls how this fiber is fibered over CP2. As I say, the metrics are known and they are smooth if Q is in some range. However, we will not need the metric because toric geometry is powerful enough to allow us to derive everything without knowing the metric. Moreover, the cone is in fact a toric Calabi-Yau 4, and here is the toric diagram. So it's similar to the one before. In particular, here there are p plus 1 vertically aligned points. So p controls the height of this point here, and q controls the height of this point here. This point can be at various heights, and q controls this. Okay, so this Calabi-Yau 4 has some number of Crepin resolutions. This number is p. One corresponds to blowing up a CP2, which is shrinking at the tip of the cone, and the other p minus 1 corresponds somehow to resolving some 6 cycles that arise because the fiber is this length space. In the toric diagram, that corresponds to these internal points that are white instead of blue. Okay, and then we can choose some U1M in such a way that if you do the Keller quotient, the Calabi-Yau 3 that we get is C3 mod Z3, which is, this triangle. However, on top of this, we get also PD6 branes. So it's precisely what I described before. We get this very simple and very well-known Calabi-Yau 3 with PD6 branes wrapping this CP2 at the tip. Okay, this example is also interesting for another reason, which is related to torsion. because if we look at the cohomology of these Sarakin-Einstein manifold, in particular the fourth cohomology, so this fourth cohomology is pure torsion, in this case, a group that I call gamma. So this is a finite abelian group, which is obtained if we take a lattice in Z2, so we have a two-dimensional lattice, and we mod out by two identifications. So it's a sort of torus inside this Z2. This is our torsion group, and then it has some number of elements, which is this one. So in particular, it means that in M theory we can put a torsion flux taking value in this group, and for each of these choices we should get a different field theory. Okay, so I want to apply what I described before and get the field theory. Now, the only ingredient that I didn't explain so far is what to do with torsion. In particular, we want to understand what happens step 2a when we start with some torsion in M theory. Okay, so I will not describe the most general case, which probably is very complicated. I will describe what happens in this particular case. So if you have torsion, pure torsion, the flux is 0. So torsion can be understood as a flat connection for the C3 potential. So in particular, when we do the reduction, in type 2a, the form from flux is 0. However, this flat connection ends up being a flat B2, so some flat connection for the Navier-Schwarz potential. And it turns out also to be quantized, just because we started with something that was quantized. And one would like to understand why this B2 is quantized, because in general, in string theory, the period of B2 is not quantized. Okay, so so we would like to understand first why there is this quantization, and then how to interpret this B2. And the answer comes from looking at page charges. Page charges or page Ramond-Ramond fluxes are constructed out of the usual Maxwell Ramond-Ramond fluxes of type 2a by twisting by the B field. So suppose that this is a polyform. Here I have all the Ramond-Ramond fluxes. I take this wedge and I read off some so-called page Ramond-Ramond fluxes. Now, Maxwell charges are the usual charges in type 2 supergravity. They are gauge invariant. However, they are not sourced just by the branes. They are sourced by the branes, but not only by the branes, because if we have some fluxes in the bulk, the differential of the Ramond fluxes gets contribution from the fluxes. So they do not see only the branes, and for this reason they are not quantized. On the other hand, if we construct these page charges and we compute the differential, the terms in the bulk cancel, and they're only sourced by the branes and the fluxes on the branes. So in particular, they only see the branes, and for this reason they're also quantized. However, in order to have this nice object, we have to give up gauge invariance, because these page charges are not gauge invariant. And if you do a large gain transformation of the B field, since these are gauge invariant, you see that the page charges are going to change. Okay. But now, if we look at the 4-page charge, which is given by this quantity, in principle there is another term if we have F0. By my example, I don't have F0. F4 was equal to 0. So we see that the 4-page charge, since there is some F2, is precisely counting the period of B2. So instead of measuring the period of B2, we could alternatively just measure the D4 page charge here. And moreover, then we also understand why this B2 is quantized. It's somehow dynamically quantized because these page charges are quantized, and since this is 0 and this is quantized, also B2 is quantized. So it's a dynamical quantization of the B field in this case. Okay, so one could also go beyond this symbol check and check that in fact precisely this torsion group is reproduced in type 2a. So first of all, one should look what are the 4 cycles in the type 2a geometry, and there are 2. So the 4 page charges, they are quantized, so we get 2 integers that reproduce this Z2 here. But also, as I said, they are not gauge invariant. So if I do a large gain transformation, I get different charges, but actually they are identified with the original ones, and the periodicity so the periodicity of the B field precisely reproduces the periodicity here. So the moral is that at least in this example, torsion flux in M theory precisely goes into a lattice of page charges in type 2A. Okay, so essentially now we have all the ingredients because we have type 2A geometry. We have some D2 and D6 charges in type 2A. They come with the D2 from the reduction, the D6 charge from the D6 branes, and the D4 charge counts torsion in M theory. Okay, so now if we apply this to the quiver, as I said before, essentially what we have to do is that, okay, we have point like branes at a Calabi-Yau 3. We know that this is going to break into fractional branes. I will call each fractional brane as U1V. They can be identified with some shifts on the Calabi-Yau 3. Each of them will have some charges, D2, D4, and D6, which are given by the rank, the first and the second, or the first chain class and the second chain character of this sheaf. And so each of these corresponds to one node in the quiver, and there is a linear relation between the charges and the ranks in the quiver. These can be worked out with various methods in algebraic geometry, but this is a very simple Calabi-Yau 3, so this has been worked out long ago. And so in particular for this case, well, the quiver is a 3-node quiver with 3 bifundamentals connecting them in each of these pairs. There is some known superpotential. And also, more importantly, what is known is the so-called dictionary. So the dictionary tells us precisely which is this linear relation between the charges and the ranks. The dictionary is just a matrix, and essentially each line in this matrix is just tells us what is the D6, D4, and D2 charge of one of these fractional branes. So in general, this dictionary is not a square, it's a long matrix with 3 columns, and the first column is what is the D6 charge of each of the fractional branes, what is the D4, and what is the D2. And so now applying what I said, one can, well, okay, as I said, precisely this dictionary tells what is the relation between the charges and the ranks, and substituting inverse domino action, also the Chen-Simons come from the same matrix. So also this charges determines what are the Chen-Simons. Okay, so one can easily work out what the field theory is, and in this example one gets something like the following. So there are the 3 gauge groups that corresponds to the quiver that I drew before. The ranks are in general function of n, which is the number of M2 branes, P and Q, which comes from the geometry, and N0 and 1, which parameterize the torsion. So here in general, they affect both the Chen-Simons and the ranks of the quiver. And okay, here there are some subtleties that I'm not going to mention, but in particular that in different range of parameters one gets different formulae. But for instance, one can check that there is precisely a one-to-one map between all possible geometries with torsion fluxes and all possible assignments of numbers in the ranks and the levels. So there is a realization of this one-to-one correspondence between all possible torsions and a family of field theories. Okay, is there any question? Okay, so this completes what I wanted to say about the first problem of having a way of determining the field theory, and then I would like to say something about how to compute the modular spaces. In particular, okay, we had a derivation of this field theory, but we want to know whether, I mean, we want to do some checks on this, and for instance, see whether the Calabi-Yau 4 is really containing the modular space of these theories. Okay, so okay, the complication is essentially what I described at the beginning, is that there are monopole operators. These monopole operators are defined as some boundary condition in the path integral. In particular, one imposes if there is some monopole operator at some point x equal to 0, that there is some flux around this point, and there is some quantization condition, which is the usual GNO quantization. And these monopoles can be made supersymmetric in an n equal to theory. In particular, they are half BPS. Now, as I said, these monopoles, they are classically charged under the topological symmetries. They can also have classically some gauge charges if there are Chern-Simons terms. And so classically, these are all the charges they have, but at one loop, they can get other charges. In particular, they can get all sorts of charges. They can get extra gauge charges. They can get abelian global charges or R charges. And they can even be charged under hidden symmetries if there are. And actually, well, one can compute the one-loop contribution. In general, just for monopole operators, there will be, well, in principle, one expect contribution all loops. But at least in n equal to superconformal theories, one can prove with localization that the one-loop answer is exact. Essentially by doing, computing the expectation value of the charge is a monopole background. And one gets some formulae like this. For instance, suppose I have some abelian charge, I want to compute the one-loop correction. This is just a sum over the fermions of some contribution. So, okay, in this case, it's a sum over the weights of some representation. But what is important is that this fermions has to be charged under the abelian symmetry. So essentially what happens is that since the monopole can have zero modes, if these zero modes are charged under symmetries, then the monopole gets the charges of the zero modes. So how does this affect the chiral ring of the theory? Well, the chiral ring is Q closed modulo Q exact operators, and at least classically, how do we compute the chiral ring? We take the ring generated by all chiral operators in the theory, and then we mod out by the ideal, which is generated by derivatives of the superpotential. However, here, as I said, there are two modifications. One is that we should include the monopoles in the generators. And the other one is that there can be some quantum relations in this ideal that involve the monopoles. Now here the problem is that, so one in principle should just compute all the monopoles, which are BPS, and compute all the relations. But in general, it's very hard to compute this. One can try to do some assumptions and see whether this is something consistent. So first of all, one can consider the subring, which is generated just by these very simple diagonal monopoles that is considered at the beginning, T and T tilde. Then one can compute the charges of this T and T tilde with the formula that I had before. And then one can try to write down all possible relations of this sort in which P1 and P2 are fundamental fields in the theory, such that, all possible relations which are compatible with the symmetries. In general, one expects that if these relations are compatible with symmetries, might be there. So one can try to consider the following ring, which is given by, okay, it's generated by all the operators, the chiral operators and the monopoles, and then it's divided by the ideal, which is given by the superpotential, and all these relations, which one can write down. And one can try to study this object and see what this is. And so in particular, we can try to do that for the theories that I presented before. And so, okay, essentially I already said what one is going to do. So there were 3 gauge groups with some Chern-Simons. So first of all, well, there was some superpotential to do I wrote before. So there are some F-term relations. One can compute the monopole charges and can write down there will be some relations involving the monopoles. So here T tilde, while these are the fields in the quiver. And then, yes, one write down gauge invariance in terms of all these fields and impose some relations. And at the end of the day, during this exercise, one precisely finds an algebraic description of this Calabi-Yau PQ that one started with. So this procedure at least in this example, works. And in particular, notice that if one tried to compute the classical moduli space of these quivers, one would not have obtained this geometry here. So the one-loop corrections are really important to get the correct geometry. Yes. So you can go in radial quantization, and then you explicitly construct them. So you have R times S2, you put the flux, and then you have the BPS equations, and you see that you have to turn on some scalars, and they are BPS. And of course, when you quantize it, then you have these zero modes, which give at one loop the charges to the monopoles. Any other question? Okay, so in the last minutes, I'll try to say something about, so this was the first check in my list. So seeing whether the Calabi-Yau 4 is contained in the modular space. Another check was whether actually the Krepan resolutions of this Calabi-Yau are contained in the modular space of the theory. So this is the thing I want to look at now. So what happens in 4 dimensions, for example, if you have D3-branes at Calabi-Yau 3, also there, Calabi-Yau 3 in general has some resolutions, and one would like to see this resolution as some modular space of the 4-dimensional theory. So what happens in that case is that essentially Fayet-Iliopoulos terms contain all possible resolution of this Calabi-Yau 3. Now, really in 4 dimensions, the theory is SUN, so you should not talk about Fayet-Iliopoulos terms. They are really just solutions of the D-term equations. But if one thinks in terms of UN gauge group, then these are the Fayet-Iliopoulos terms. So one can think that, okay, in this case, it happens it works in the same way. So the Fayet-Iliopoulos terms precisely describe all the Krepan resolution of the Calabi-Yau 4, but this is not the case. And we immediately see it in this example, because, for instance, in this example, the theory has 3 gauge groups. So at most, there are 3 Fayet-Iliopoulos terms. But as I said at the beginning, there are P Krepan resolution of the Calabi-Yau 4. P can be as large as we want. So, of course, the Fayet-Iliopoulos terms are not enough. Okay. So now, in order to analyze this question, I will turn to a different way of computing the modular space. Instead of using the monopoles, one can do a semi-classical analysis that contains one-loop corrections, and this analysis gives the same result. I think essentially because the one-loop charges of monopoles were exact. So in this case, the one-loop analysis gives, at least at the level of complex structure, the correct answer. So how does this semi-classical analysis works? These techniques have been already applied long ago. Okay, so again, suppose we start with some quiver gauge theory. So we have a product of gauge groups. They don't have all the same ranks. So let me call n the minimal rank, and then mi are the offsets. Now, suppose that now we go on the Coulomb branch. So in the vector multiplet here, there is a scalar which is real in the joint representation, and we can give it a vev. And this is our Coulomb branch. So let's give a vev to these real adjoint scalars, and I divide them in 2 groups, sigma, which are the ones which represent the Cartan of these first n directions. So they are common to all the groups. And then the sigma tilde, the ones that belong to these extra directions. So for some groups, there will be a sigma tilde. For some other groups, no. And their number will vary. So generically, when we turn on all these fields, the gauge rule is completely broken to the maximal torus. So there will be a bunch of U1s. How many? Well, there will be n times the number of gauge groups in the quiver. And then there will be some extra U1s that comes from the fact that the ranks are not all the same. In particular, the gauge theory, if we take this sigma I among the different groups, to be equal, so we take a diagonal configuration in which in each gauge group we take the same sigma, but along gauge directions they can be different. Then really the theory is broken to n copies of the abelian quiver, and then there will be some incomplete copies. So I'm not sure I've been clear, but essentially what I want to say is that we have this quiver, so we give some diagonal value to this sigma. In general, this breaks to n copies of this quiver, and then there will be some incomplete copies because the ranks were not all the same. In particular, if mi was 0, we don't get a contribution from that group, but if there is some other mi, that will contribute to these incomplete copies. Okay. And now we want to see what is the modular space of this. So let's focus on one of these abelian copies. So I just have the abelian quiver with groups U1. However, here the important point is that when we break the gauge group to these abelian quivers, in general there are fields, bifundamental fields, which are massive. We have to integrate them out. They get real masses. And when we integrate them out, there is a one-loop shift of the Chern-Simons level. In particular, here is the determ equation that I get for the abelian quiver. And let me explain what is this. So here, there is the usual determ in terms of the bifundamental fields. Okay. Now, on the right-hand side, in general, there can be Fayet-Iliopoulos terms, the Baire-Fayet-Iliopoulos terms. There is a contribution that comes from the Baire-Chern-Simons term. And then there is some contribution that comes from the one loop. This is a sort of effective Chern-Simons that one obtains integrating out these fields. In particular, the fields that were connecting one of these groups with one of these groups. And now in here, you see what appears here is sigma tilde. Sigma tilde are the adjoint scalars in these incomplete copies. So the result is that here we have many more parameters. We don't have just the Fayet-Iliopoulos terms, but we have all these parameters, and precisely the adjoint scalars in the incomplete copies play the role of resolution parameters for the Calabi-Yau 4. Now, I don't have time here to go into the details, but one can work out actually very precisely this equation, and one can see that precisely this sigma tilde describe all the Krepan resolution of the Calabi-Yau 4. So this is the first thing. On the other hand, so this sigma tilde describes the Krepan resolutions. On the other hand, one should also look at what is the dynamics of these incomplete copies, and it may or may not happen that these sigma tilde are flat directions. So when they are flat direction, it means that the Calabi-Yau 4 can be resolved. And for instance, if one to consider the M-theory geometry without form flux, without distortion flux, one expects that all the Krepan resolutions are there, and this is what happens. But more generally, if there is torsion in M-theory, this torsion can be an obstruction to the presence of these resolutions, because just if there is torsion, the resolution is no longer BPS. And the dynamics of these incomplete copies, in that case, precisely reflect this, because one gets that the sigma tilde are frozen to 0. So in that case, one precisely see this geometrical, the realization of this geometrical fact that torsion flux obstructs resolutions. Okay, I think I will conclude here.
Are there any questions for Francesco? If there are no further questions, then let's thank you. Stop.